All right, so for this first one, we have a conceptual question to start, and what we're asked the first time is we want to compare these three rocks that are thrown horizontally from some height. We see that both rock A and B are thrown at a speed of 5 meters per second, but B is thrown from twice the height, and rock C is thrown from the same height as A, but at 10 meters per second. So first we're asked to compare rock A and rock B here, and so I'm going to start with that. So which one is going to hit the ground first? Rock A would hit the ground first in this situation. And here's what I would say. The basic idea is that both objects are thrown horizontally, which means their y initial, okay, or VIY, is 0. And that's actually true for all of them. So the thing that ultimately is going to determine how long it takes to hit the ground is their height. Okay, so they all have 0 initial y velocity. They all are accelerating down at 9.8 meters per second squared. We, of course, know that is true for any object that's a projectile. So the thing that ultimately determines how long they're in the air is their height, and since B is a greater height, it will hit the ground first. All right, moving on to the second part here. We're now comparing rock A to rock C. We know which one will hit the ground first in that situation, and so we notice that those two are thrown from the same height. And basically, the same argument can be made as we made in A, but now it's going to be the same time. Really, the big idea is, once again, both rocks have the same initial y velocity and an acceleration of 9.8 meters per second squared. Since A and C are thrown from the same height, they'll hit the ground at the same time. And the thing that I might add is that even though C has a greater x velocity, that doesn't affect the y motion, right? And that's that idea that x and y motions are independent of each other. All right, so for this next one, we have an arrow being shot. It's fired horizontally, so that means a few important things. So its path is going to look kind of like that. From a height that's it hits a target that's 22 meters away. So there's our 22 meters, and it's fired from a height here of 0.95 meters. So I'm going to go ahead and start filling in the chart with the things I know. Of course, I always know that AX is 0, and AY is going to be negative 9.8 meters per second squared. That's true for any projectile. The fact that it's fired horizontally tells me VIY is 0. And then I also know my delta x is 22 meters, and my delta y is 0.95 meters. That is, though, going to be a negative because I'm losing 0.95 meters of height. So I want to make sure I set that as a negative 0.95. So the first thing I'm going to do here is I'm going to use my y side, because I know all this information, to ultimately figure out my time, which I can then bring over to my x side. So I'm going to start with the delta y equals VIYT plus 1/2 AYT squared. So I can say negative 0.95 equals 0 times t plus 1/2 times negative 9.8 times t squared. This first term here just goes away because it's 0 times t. And what I'm left with is negative 0.95 equals negative 4.9 times t squared. That means when I divide by 4.9, I get 0.193 equals t squared. Square rooting both of those sides, I find that t is 0.44 seconds. So I can plug that in here to my x side. All right, and then I can go ahead and use that now to solve for the initial velocity. So I'm going to use actually the exact same equation here, but obviously we're going to be using the x information. And so first thing I'm going to do is I'm just going to cross off that final term because I know that a is 0 in the x direction. And so what I'm left with is 22 equals VIX multiplied by my time, 0.44. I divide by that 0.44 and I get that my time here, VI, is going to be 49.96. So if you rounded it to 50, that would be fine, meters per second. All right, and that's going to be the x velocity the entire time because we know that it's constant. Alright, so we move on down to this one, and here we have a discus being thrown at a velocity of 22 meters per second at an angle of 31 degrees. So what I'm going to do, obviously I can of course fill in my two accelerations first, 0 in the x and negative 9.8 meters per second squared in the y. But after doing that, I'm going to go ahead and use that velocity and that angle to solve for the initial velocity in the x and the y directions. Okay, and so I know that VIX here is going to be 22 times cosine of 31, okay, because it's the adjacent side, which gives me an x component here of 18.86 meters per second. And in the y, it's going to be 22 sine of 31, which gives me a y component here of 11.33 meters per second. So I can go ahead and plug those two in here. So this is going to be 18.86. And that's also going to be the final, because of course it's traveling at a constant speed in the x direction. And then in the y, it's going to be 11.33 meters per second. The next thing I'm going to do is I'm going to think about this flight path. So I know my object starts here, it goes up in the air, and it returns to the same height that it was thrown from. So that means I can say at my peak, my y velocity is 0, and when it returns, that y velocity is going to be a negative 11.33. I also could use some concepts that I know about delta y. For example, that's 0 here, but this is enough. So what I'm going to do is I'm actually going to take this time at the peak and use that to solve from there. It's not the only option you have here. There are a few other ways of doing this, but I'm going to set that final y velocity to be 0, all right, and go from there. So what I can then do is I can say VFY equals VIY plus AYT. Use that equation to solve for my time. So 0 equals 11.33 minus 9.8t. I can move that 11.33 over, so negative 11.33 equals negative 9.8t. So I get a time here of 1.156 seconds, but that's my time to the peak, all right? If I want to find my total time, which is what this is really asking about, just how long is it in the air, I'm going to multiply that by 2, because the time to the peak is half the total. And so I get that the total time in air is going to be 2.31 seconds. And there's my final answer for the first part. For the second part was the horizontal distance traveled by the discus. I'm now going to go to my x side. I'm going to use that total time that I just found because I want the total horizontal distance traveled. And I'm going to use my delta x equation. So VIXT plus 1/2 AX t squared. I know that x acceleration term will go away because a is just 0 here. And so what I'm left with is delta x is going to be equal to that 18.86 times 2.31. And so I end up getting an x displacement here of 43.6 meters. All right, so moving on to this next one. Here we have a student jumping off of a diving board with an initial velocity of 4 meters per second and an angle of 60 degrees above the horizontal. And the diving board is 1.5 meters above the water. So we're not having a symmetrical launch here, and we'll talk about that in a second. First, of course, though, we can fill in our accelerations, 0 in the x direction and negative 9.8 in the y direction here. So I'm going to go ahead then and take that velocity and angle and break it up into x and y components. So here I have that 4 meters per second at an angle of 60 degrees. So when I go and break that up into x and y components, I find my VIY is going to be 4 sine of 60, which gives me a VIY here of 3.46 meters per second. And in the x, that VIX, this component is going to be 4 cosine of 60, because it's the adjacent side. So Vix is going to be equal to 2 meters per second. So I can take those two and I can put those in for my Vix and my Viy. Now, what I want to think about is, once again, I'm going to draw a quick sketch of the motion here through the air, and we're going to think about what other concepts we know in this situation. So my flight is going to look something like this. I start here, I fly up to some maximum height, and then I land in the water down here, and that's going to be a distance of 1.5 meters. Okay. If we're thinking about that maximum height, right, that's occurring at this point here. So that is going to be a y velocity of 0. Okay, maximum height is going to be a y velocity of 0. And so what I can do from there is I can use that in my y equation to solve for my delta y. So I'm going to use this time the VFY squared equals VIY squared plus 2AY delta y. So I can say 0 squared equals 3.46 squared plus 2 times negative 9.8 times delta y. And so I end up getting 0 equals 12 minus 19.6 delta y. And so I find that my delta y here is 0.612 meters. All right, moving on to the second part here, I'm actually going to take basically the exact same setup that I had up here, and I'm just going to move that on down. But what we're doing now is we're going to be thinking about this point when we land here, okay, which is this point right here, and that means that that VFY will not be 0, but I do know that at that point my delta y is going to be negative 1.5 meters. So using the exact same setup, but I now have a delta y of negative 1.5 meters, and I can go from there. So in order to start this one, I'm first going to think about finding my time. I may recognize that this setup here in my y direction will lead to a quadratic. So what I'm going to do is I'm going to first find my final y velocity and then use that to solve for my time. So I'm going to say VFY squared here equals VIY squared plus 2AY delta y. And so I can sub in what I know. So I don't know my final y velocity squared because now I'm thinking about the very end. I do know my initial is that 3.46 plus 2 times negative 9.8 times negative 1.5. We do want to make sure it's negative because we're landing below the spot where we started. And so I find that Vy squared is equal to 41.4. Taking the square root of that, I get that VFY is 6.43, but I have to consider whenever I do this square root, okay, of VFY squared, I have to think about my signs. Because this is going down, it's going to actually be a negative 6.43. From there, I can go ahead and solve for my time. So I can say VFY equals VIY plus AYT, still using the y stuff, of course. So I have negative 6.43 equals 3.46 minus 9.8t. So negative 9.89, when I subtract that 3.46 over, equals negative 9.8t. I divide and I find that my time here is going to be 1.01 seconds. I can now use that time in the x direction to solve for my horizontal displacement. So I have delta x equals VIXT plus 1/2 AXT squared. That x entire side goes away because a is 0. And so I end up getting that delta x equals 2 times 1.01. So that means my overall horizontal displacement is 2.02 meters.